This video will continue in section 11. We'll talk about the sum or difference of cubes. Part 1, we talked about the difference of squares. We pointed out the sum of squares does not factor. And now in part 2, we get to the sum or difference of cubes. Still have nice binomials, but now we realize that either plus or minus, they each have their own factorization formula. And the second thing, this is where I think for a lot of people, it really benefits to write out your A and your B. It's one thing when you're just doing difference of squares, A minus B, A plus B, you identify A and just plug in very simply. But here, as you plug in, it starts nice, but then you end up with A squared. You end up with A times B. You end up with B squared. So it's very easy to make some mistakes as you plug in, so you might want to be just a little more thorough and literal as you match your formulas, so to speak. Second thing, just like before, if we're talking about cubes, we want to recognize nice perfect cubes. So for variables, similarly, x cubed, y cubed, those are perfect cubes. As far as numbers, well, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. Our book pretty much stops there. They definitely want you to know 1 through 10 squared, but for cubes, they get a little bit bigger for the numbers, so 1 through 5 cubed is typically enough. But then similarly, as we saw for squares, variables, when they have the perfect exponent, is just so nice and easy. But to realize x to the 6th could be treated as x cubed squared. X to the 9th, x cubed cubed. X to the 12th could be x to the 4th cubed. What we saw for variables, as long as the exponent is even, it could be treated as a perfect square. And as the exponent can be divided by 3 cleanly, then we can treat it as a perfect cube. So the identification isn't quite as easy, but again, especially when you focus on the numbers, 64 in particularly can be troubling because 64 is 8 squared. It's a perfect square, but it also is 4 cubed, so it also serves as a perfect cube. But these numbers need to stand out and these exponents. So now I'm going to jump right in. The formulas, if we actually multiplied them out, we'll see so much cancels, which is why these simplify down so nicely. And your formulas, they are so similar. So it's so easy to goof them up. Some people accidentally, because this is a plus, they try and make everything a plus, and then this is a minus, so they make that a minus and that a minus. But you got to be careful. The plus here goes with the plus in the first term. The minus here goes with the minus in the first term. Then everything else is the same over here, except when this was a plus, this was a minus, and when this was a minus, this was a plus. The point is simply this. Again, for the online people, you could always look up your formula in a pinch. But for people who are trying to memorize this, this matches in the front, and then you need the opposite sign here. That's kind of the easier way to memorize it. But now let's practice. Let's jump in. Let's factor. Number 1, let's start off with x cubed plus 125. I see a perfect cube. If that's a cube, well, I'm sorry, let me go backwards. I don't see a GCF. We should always remind ourselves of that. We always think about GCF first. There is no common factor. What else can I do? It's a binomial. Hey, it looks like it might match this form. The x is a perfect cube. What about 125? We just noted that. That is 5 cubed. So similarly, like we said for difference of squares, x cubed is a cubed, so that just makes a plain x. B cubed is 5 cubed, so b is just 5. So as I go through my formula, a plus b, my factorization starts x plus 5. And then in my second part, A squared, well, A is x. A squared will just be x squared minus A times B. Well, A times B, x times 5. We more traditionally write that as 5x, not x times 5, but that's our middle. And then B squared, 5 squared, will give me a 25 on the edge. Now, before we keep going, we want to make a very important point here. This first problem just says factor. After a couple of problems, I'm going to say factor completely again, and we'll get back to seeing multiple steps for factoring. But right now, I do this factorization. That feels good. I look over that. That's a nice trinomial. So that's where people have so much temptation, like, oh, I got to keep going. The grouping number, 1 times 25 is 25. What are the factors of 25 that add to 5? Well, 1 and 25 adds to 26. That's not it. 5 and 5 add to 10. That's not it. And there's no other factors of 25. Here's the thing to remember, everybody. You look at these formulas, that second part, whether it's sum or difference of cubes, that second part has nice trinomial feel to it every time. But here's the key, everybody. It will never factor. Every time you try and do something like that, you would end up in this situation. It feels like I can't do anything because I can't. So here's 2 important lessons. Number 1 is that when it applies specifically here, these will always have temptation. But if these factored further, folks, we would do it in the formula. But they never factor, so that's done. But the second thing is just to realize there are nice trinomials that don't factor. Some people just get in the groove of, well, they all factor. And when you're working with problems from class, you are getting problems that factor. I'm not trying to trick you and say, here's one that doesn't in the middle of ones that do. But we want to have that recognition, especially here. And it can happen in other places too, but especially here. Very tempting to think that keeps going, but you are done right here. That is the answer to number 1. Let's keep going. Number 2, 8x cubed minus 64y cubed. I look at number 2, and if you are following along in section 11, part 1, you saw almost the same thing. In number 1, one component was a variable, one component was a number, and then in problem number 2, they both have variable and numeric components. But just like in difference of squares, they could have both. X is cubed. Here I see a minus, I see a binomial, I see 64, that's 8 squared. So I might for a moment think about this as a difference of squares, but that's not a perfect square. That's not a square. That's not a square. So I got to realize, oh, wait, I've got perfect cubes here. 8 is 2 cubed. 64 is 4 cubed. So in this one, oh, I'm sorry, folks. I actually didn't want this. I could take out a common 2 here. That would have been the easiest thing. Take out a 2 right off the bat. I'm sorry. Actually, it's a common 4. No, it's a common 8. 8 would be the GCF here. I didn't want that to happen. Let's make that a 27. I don't want a coincidence here. So 27x cubed is 3 cubed x cubed. So A would be 3x. B cubed is 4 cubed y cubed. So B would just be 4y. Now I'm following this formula because I've got the difference instead of the sum. So following this formula starts nice. A minus B, simple 3x minus 4y. But now you see over here, I did multiplication and clean this up as I plugged in, but now it could look very messy. So I'll just be very literal as I plug in. Next comes, here, a squared. So I'll get quantity 3x squared. Plus a times b. So I'm getting plus 3x times 4y plus b squared. So plus 4y quantity squared. It's one thing when your terms are this simple to just be able to square x, to be able to multiply 5 times x together. But here it's just a little bit more. So instead of trying to get caught doing too much in our head, like simple things here, people square the x but forget to square the 3. Little things like that definitely creep up. So just to write it out. And now clean up our answer. This part was already clean, 3x minus 4y. But over here, 3 squared is 9. X squared is x squared. 3 times 4 is 12. And I still have the xy. 4 squared is 16. And I still have the y squared at the end. Now I've got more variables, but the variables still follow a nice trinomial form. So just like we said back in number 1, there's a lot of temptation, and at least in number 1, your grouping number was only 25. There's only a couple of factor pairs to look through to realize, oh, nothing works. Here, 9 times 16, that's 144. There are so many factor pairs to go through, only to realize none of them work and how much time you wasted. So one more time, the bigger thing, when you know you are using the sum or difference of cubes, that second part won't factor any further. Let's keep going. Number 3. In number 3, let's look at x to the 6th minus 125 y cubed. Well, again, I see 2 terms. I don't see a GCF. I don't know what I'm looking for initially, but then I look over here. X to the 6th, not obvious. It's a high exponent, but I come over here, 125. I recognize that as a perfect cube. Y cubed, that is already definitely a perfect cube. So if 5 cubed y cubed is taking this second spot, that looks like a perfect cube. Can I treat this like a perfect cube? We can. That's where it wasn't obvious right off the bat, but once I realized I wanted perfect cubes here, that's when I realized I can make that x squared cubed. Oops, I wrote that backwards here. I wanted x squared cubed. So now in this one, a would be x squared. B would be 5y. Once again, not simple terms, but when I start to plug into the formula starts simple enough. A minus b, so x squared minus 5y. But then the rest starts getting messy, so again, I'll just write it out and then clean it up. I get x squared squared, a squared. It's so easy to miss this square because you already had one, but a itself was x squared, and now you need to square that. So that's what I mean. It's so easy to lose things, have little mistakes here. So know yourself, but most of us need to be very technical and methodical to make sure we don't make little mistakes here. Plus a times b plus b squared. First part, nothing extra to do there. That was nice. But here, x squared squared is x to the 4th. This one, 5x squared y would be the best way to multiply those. And then here, 25y squared. Don't forget, you are distributing that exponent. 5 squared is 25, and then the y squared at the end. All right, 2 more. So we've got our formulas, 2 more. Now let's factor completely. Let's factor completely. Let's look at problem number 4. 4x to the 5th minus 32x squared. I look at this one. Okay, nothing too crazy going on here at GCF right off the bat. I don't see, I mean, this is a binomial. I see a subtraction sign. I guess maybe I see a square here to think about squares. And the 4, I suppose, might do that as well. But that's not a perfect square. That's not a perfect square. But I do have stuff in common. 4 and 32 share a common 4. X to the 5th x squared have a common x squared. 4x squared comes out. X cubed minus 8 is left behind. Well, if x cubed minus 8 is left behind, now I've got perfect cubes. X is cubed minus 8 is a nice 2 cubed. This one is almost as nice as problem number 1, but we had to do the GCF first. Up here, I've got A is x, B is 2, so I get A minus B, A squared plus AB plus B squared. And now, even though this was multi-step factoring, this nice trinomial still ended up in my answer, and there's still some temptation. But one more time, it came from one of these two. It's done. Nothing else to be done. That is a full answer. Number 5, I think I said 2 more. It was 3 more. 3 more. Number 5, let's look at 64 x to the 4th y squared plus xy squared. Again, kind of tempting in a variety of ways. 64 can be a perfect square. That can be written as a perfect square. That's a perfect square. That's a perfect square. But there is no sum of squares formula number 1, and that x is still in the way. So many pieces look good, but the plus was a surefire way it's not working, and that x is just another reason. There's no squares here to help us. But one more time, we start with GCF. I see common x's, 1x comes out. I see common y's, y squared, that y squared comes out. 64 is still left, 1x came out, so x cubed left, y squared is out, plus here, the xy squared is entirely out. What's left? Something has to be left there. I'm left with the 1. So, where do we go from here? Feels good, but now I look at that binomial. The plus is still there, but I see the cube now. I'm thinking sum of cubes. 64 is 4 cubed, so I can look at A as a nice clean 4x, right? 4 cubed x cubed, so A cubed would just be the 4x. But then this throws some people off, but don't forget, again, it's easy to miss this, because 1 is 1 squared is 1 cubed. 1 to any power is 1. So 1 can be a perfect anything. 1 is 1 cubed. B would just be 1. So the xy squared still there. A plus B becomes 4x plus 1. And then the a squared minus ab plus b squared. My a squared, 16x squared. I'm doing the squaring this time. A times b, 4x times 1 is just 1. And then b squared, 1 squared is also 1. That is my final answer. And last but not least, let's look at x to the 6th minus 64. Because what happens in this one is a little interesting. I see my perfect cubes. There's also a way I could look at this as perfect squares, but let's look at this as cubes. 4 cubed, x squared cubed. I got a is x squared, b would be 4. So I'm factoring, and unlike the other two where GCF was necessary first to make this difference of cubes. To make this sum of cubes, this one didn't have a GCF, was already difference of cubes. I follow my formula, a minus b, x squared minus 4, then x squared squared plus x squared times 4, and then the 4 squared. A squared plus ab plus b squared. And that's typically where we say, okay, let's clean that up a bit. So I get an x to the 4th, I get a 4x squared, I get a 16. For about the 4th time in this video, we see that as a nice trinomial, but we know that doesn't factor. We feel good about our answer, but then we check and we realize something's missing. This part can still keep breaking down. The x squared minus 4, that is an a squared minus b squared. A is x, 4 is 2 squared, so this time it's this part can keep going. The x to the 4th plus 4x squared plus 16 is all good, but this one, a minus b will give me an x minus 2, and a plus b will give me an x plus 2. So not trying to get too tricky here, just trying to point out big picture that there are so many different interesting ways these techniques can all combine. So you really want to make sure you've got a lot of practice individually with each one, and then see the practice of mixing them together. But when you mix them together, the GCF is what comes first. From there, anything can happen. We've seen trinomials, which then end up with difference of squares, and all kinds of things can happen. But that's what we can establish as our starting point. Start with GCF first, and our second big thing, always make sure, even if we've successfully factored, always make sure to check to see if there's anything more we can do.